computational physics, how and also why. Right? So why would we need to use computers or numerical? Okay. So computational physics, I'll use computational and numerical interchangeably, and hopefully we'll see why. So let's start with the Newtonian approach to physics in general. Right. So what does it mean? What does Newtonian physics mean? Well, what we want is, and for simplicity, we can think about, forces, kinematics. So forces, accelerations, velocities, positions. These can also apply to more abstract things like, how a temperature varies over time or something like that. But I think to make it concrete, we'll think about mechanics for now. So what we want is a trajectory, right? Where the object and where it is and how it's moving, which means velocity, really, at all times. So what do we know? In the Newtonian approach, what we focus on is forces, right? And the main tool in doing Newtonian physics is F equals ma, right? So if you know the force, then you know the object's mass, then you know the acceleration. Okay, now this, in your introductory class, you just treated this as an algebraic equation. Really, this is a differential equation because the acceleration is the second derivative of position. Okay, so so what that means is we're not just solving for an unknown algebraic variable called an acceleration. We're saying, what does this acceleration do to these other quantities, right? The velocity and the position specifically. So we take that acceleration and we want to find the velocity and we want to find the position. And so what we're really doing is we're adding up small changes, right? Because what is an acceleration? It's a change in velocity over a change in time. Or if we rewrite that, I can say, well, if I take that acceleration that I know, multiply it by a small change in time, it's going to give me a change in velocity. And similarly, velocity is a change in position, right? So velocity is change in position over change in time. So I can rearrange that and say, if I take my velocity and multiply it over a small increment of time, that's going to tell me how much the position of my object changes in that small increment of time. Right, so that's the definition of those quantities, right? And so the question then is, how do you add up all these little changes? Right, so anybody have an idea if you have a bunch of little changes and you want to add them up over a bunch of little increments of time, what does that sound like?
Taylor series?
Taylor series is more related. I mean, it's kind of related there, but it's more about trying to get the value of a function. But okay, so it's something to do with calculus. Integration, right? So if I say calculus, it kind of narrows it down to I mean, Taylor series, it's kind of its own thing, but is it a derivative or is it an integral, right? And a Taylor series would work for if we only care about, if we know something here and we only want to take one small step, right? But if we want to take a bunch of little small steps, we would want to integrate, right? So that was Newton's idea, right? And so, if you're Isaac Newton and you're like, well, how do I add up all these little changes? I can invent a whole new field of math and call it calculus and not really prove anything. I'll leave that for mathematicians to take 200 years to really prove all the stuff, but it makes sense intuitively because I'm a genius and it works. I'm speaking as Newton there. Right, so integration is a method for adding up infinitesimal changes. Right, so you would say, well, I could add up a bunch of those little delta t's, or I could take that delta t, make it really small, infinitesimally small, and call it dt. And now I'm doing an integral. Right, so if I have an acceleration, in general, if I know acceleration as a function of time, I can integrate it to get velocity as a function of time. And then if I know the velocity, I can integrate that to get the position as a function of time. Now I'm writing these as one-dimensional, but this could be, you know, if I just had taken the time to put little vector hats on top of these, it would apply for vectors as well, right? So you could say that this is in, you know, 3D or as many dimensions as you care to imagine, right? So if we have the case where acceleration is constant, this is what you spent, you know, all of last fall doing, or much of last fall doing, right? This is kinematics. So you integrate acceleration, you know, you integrate a constant, you get a constant times t, and then you have to, you know, you have to say, well, there might be a starting value that's not 0, and then you integrate that, and you get velocity times time plus 1/2 at squared, and then you might have a starting position, right? So that's where those kinematic equations come from, as you say, if you start with a constant acceleration, integrate it and integrate it again, then you get those equations. So yeah, so this is great. I mean, spend a lot of time working with this. Constant acceleration is a good approximation for lots of different physical situations. So there's, you know, there's some pros and cons to Newton's idea. One of the big pros, or I guess the main big pro, is that you get a functional form for the trajectory, right? So if you get position as a function of time, you can just write that down as a function. So at any time, I can calculate what the position is, and at any time I can calculate what the velocity is, right? And in the problems that you were doing in Physics 115, you're really only connecting 2 time points usually, right? So you might say, you know, an object starts at, you know, some launch point, and then it moves, and what, you know, so a diver jumps off a diving board and lands in the water. And so you're just connecting those 2 different times, and you want to know the position here and the velocity there, right? So you don't have to find, so if that takes, say, you know, 1.5 seconds, you don't actually have to calculate what are the position and velocity at 1 second and 1.2 seconds and 1.3 seconds, right? You can just skip to the end. So that's one of the nice things about it. The other thing is that because you're connecting those 2 time points, you can easily work backward, right? So maybe, you know, in a lot of cases when you're doing one of those problems, like the person jumping off the diving board, you know some of the initial conditions, but you also know some of the final conditions, right? You know, you're interested in when the person lands in the water, right? So you could be given the velocity at the end as an example, right? So you say she hits the water, or you could just be given the time, right? A diver jumps off the diving board and hits the water 1.5 seconds later. What was her initial velocity? You can work backward like that pretty easily. So that's good. I mean, so once you get a function, you know, you can do all that kind of stuff. So what are the drawbacks? Well, one drawback is that integrals are hard to do, right? Derivatives are easy, right? If integrals were as easy as derivatives, life would be great. But integrals are harder. And the other con is that integrals are hard, right? Some are so hard that they are literally impossible. So there might be some that you look at and say, I don't know how to do this, but somebody else does. There are some that you might look at and say, I don't know how to do this, and that's because there literally is no function that you can write down that is the answer to the integral. So I just want to say, Nick, as you seem to have connection issues, I am recording this, so hopefully you can stay connected. But you know, I will post the video on Blackboard just so that you can fill in anything that's that you might miss out on. Okay, so those are the cons, right? The math might be hard, especially if the acceleration is not constant. Maybe the acceleration depends on the position, or it depends on the velocity. So it might just be difficult for a variety of reasons. Okay, so that's the pros and cons of Newton's ideas. So if we reach a case where we can't do that integral, right? We reach an impossible integral, or one we don't know how to do, or one we just don't feel like doing, what do we do? So here is a clip from the movie Hidden Figures.
There comes a time when our dreams of the 21st century must be weighed against the realities of today.
So when I saw that movie in theaters, I was basically the Leonardo DiCaprio meme pointing at the screen when she says Euler's method. Also, there was another point where one of the other characters goes and gets a textbook on Fortran, the programming language. That was another DiCaprio meme for me. Yeah, so Euler's method, and it's when Sheldon or whatever the character's or actor's actual name was like, that's ancient. Like, come on. So is calculus, right? Calculus is older than Euler's method, and so is all this other stuff. Like, it's the Pythagorean theorem is literally ancient, right? So, whatever. That's just movie making for you. But Euler's method is a method for numerical or computational integration, right? And so this is something that you can use when you can't do the integral in closed form or by doing the calculus. So when we say numerical or computational, what we really mean is breaking down something rather than saying here's the function that tells us everything at all times. It really means do it step by step. So it's kind of like that Taylor series idea of saying, well, I know what it is to start. Let me make one small step and calculate where it would be from there. Okay, now that I'm there, take another small step. Where do I go from there? Right. So as an example here, and this is where we're really getting into writing down something new that we're going to use. Right, we said, well, the change in velocity is equal to the acceleration times the change in time. So let's say we're doing a bunch of small steps, right? We can number them: step 0, step 1, step 2, step 3, step 4. So if I'm at step number n and I want to know what the velocity is, I say, well, what was the velocity at the step just before? And then how much did that velocity change over that little increment of time? Right? So that's when I take the velocity at step n minus 1, which I would have already calculated because I started from 0 and just moved my way forward. Tick, 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 tick. And then I say, well, what's the acceleration right now? Right? It might be constant. It might depend on something else. Times that little time increment, right? And a lot of times, I mean, in Euler method, you would usually just make that time increment constant, right? So you'd say every 1/10 of a second or whatever. And so you do that, you multiply acceleration times time, add it to the old value, you get the new value, and do that again. And then with position, you do the same thing. You say, well, position is a velocity times a change in time. So you say, well, give me the old position, and then take the old velocity times the time interval. That'll tell me how much I moved in that time interval. Add it to the old position, and that's where I am now. So I'll give you a second as you're copying things down there. Now, compared to doing kinematics, you might what's different about the equation for x? What does not show up in it?
Is it 1/2 at squared?
Right. Yeah. I mean, so the acceleration's not in it at all explicitly, right? So that's the term that's otherwise it looks similar, and the velocity equation looks exactly the same, or quite similar. Yeah, but so how does the acceleration show up? It doesn't show up explicitly. It just shows up by the fact that the velocity has changed also, right? So that's the nice thing about we're just using the definitions of velocity and position and just updating them step by step by step. So, there's a lot of different ways of thinking about, how does the world really work? But if you think about, like a ball flying through the air, right? The ball flying through the air, does it think about, I'm anthropomorphizing here, right? But does the ball as it's flying through the air, does it think about, oh, well, I started here, I better keep moving this way because that's the parabola I was on? Or is it just like, here's what the force is right now, and therefore I'm going to move by this little bit because of that force, right? Here's what the force is right now. Here's how I was already moving, so here's how I continue to move, right? So it's kind of two different ways of thinking about how the physics of the universe actually works, and two different ways of approaching the calculation, right? So this is nothing fancy, and it can be done by hand. And so the real historical women who are portrayed in the movie Hidden Figures, where I had the clip from, Katherine Johnson, Mary Jackson, and Dorothy Vaughan, they were hired as what were called at the time computers, because in 1951 there were some mechanical computers, but there weren't electronic computers, what we use today. So computer was a job, and so this would have been one of the things that they did, right? As you see in the movie, Katherine Johnson quickly gets promoted into, I don't know if they call her an engineer or a mathematician, but so she would have had a lot of experience probably using Euler's method to do those integrations computationally or numerically. I remember when I was in Calc 2, we did a little bit of Euler's method by hand. But by hand is really slow, right? So what if we could make an electronic thing do those little calculations for us? That would be great, right? The other thing is that making those so if I want to say, well, what happens to this, what's the trajectory over the first 10 seconds? If I'm doing it by hand, I probably don't want to make my, I probably just want to go from 0 to 1 second, 1 to 2, 2 to 3, right? If doing more than 10 calculations sounds really tedious, right? But the smaller the delta t you make, the better your results are going to be. So that's another reason why you'd like to have a machine do it. And this is just kind of the global error, right? How far off you're gonna be at the end is proportional to your step size. So that's why this is called the first order method. So the smaller you make your step size, the smaller your error is. There are other methods that do better, right? They're called second or third or fourth order, right? So that they improve more as you make that step size smaller. And then this can easily be generalized, right? So as we start working on our spreadsheets, we'll start out with a constant acceleration, but then we will change that acceleration to include drag. And that would be really, we're not going to do that, using calculus in this class. It's a whole new method, but using Euler's method, it barely changes. So easy generalization. Okay, so let's try, a problem that we actually know the answer to. So we'll just start with free fall, right? So where the force is negative mg, right, taking upward to be the positive direction. So the acceleration is just going to be negative g. So I'm going to, before we switch to the spreadsheets, are there any questions before we do that? Okay, so, all right, thanks. So let's start with the acceleration column, because in this case, acceleration is a constant. So we can just go into that box there, the first one under A, and type negative 9.8 meters per second squared and hit enter. And then there's a variety of ways to do what's called a copy down. Definitely on Google Sheets, and I think this also works on Excel. If you bring your cursor over to that bottom right corner to where it turns into a plus sign and double click, it'll copy down and fill all those cells that are next to the where there's something in the left side column. So we've got acceleration everywhere there. Okay, so, and then for velocity, we need to pick a starting velocity. So let's do free fall starting from rest. We can put a 0 there, and then we'll start at 1,000 meters just to try and avoid hitting the ground. Okay, so now the actual Euler method part is where so if you go to that second entry for the velocity, we want to say, okay, this is going to be equal to the cell just above. So you should be able to just click, or you could type in C2. So that's our starting value. And then we're going to add our acceleration. So that's, now make sure you use everything in the Euler method refers to the previous step. Okay, so you don't want to use the acceleration right now. It doesn't matter when the acceleration is constant, but it'll keep you from having to change anything as we add other, make things more interesting. And then I need to multiply by the change in time. Now you could just say, oh, I can see that the change in time is 0.1, so you could just multiply by 0.1. But it's a good habit to get into saying, well, it's the current time minus the previous time. So I'll leave that cell highlighted there so you can see everything that's there. So that would be, in case I go back and change my time intervals, my calculation will automatically take care of that. Even if I wanted to make my time intervals spaced unevenly, it would take care of it automatically. Right, so I can go ahead and hit enter there. And then copy down. You can also, the other way to copy down is to highlight one and then drag that box down. But since there's 200 some rows, it just gets a little tedious to do that. So before even doing the position, we can make a graph. So if you highlight the time and the velocity graphs, and if you're using Excel, hopefully you know how to make a chart. But if you, on Google Sheets, you'll either see a little bar chart looking icon, or you'll have to hit the dots to see the insert chart icon. And so I'll insert the chart. And then if you hit the dots in this little box here, you can move it to its own sheet, which I always like to do just to give myself more spread out. And so you can see in this case, the velocity versus time is just a negatively sloped, velocity versus time, which is, what we know from kinematics, back last year.
What was the shortcut you used instead of dragging?
If you highlight the box, are you using Google? Okay, so if you highlight the box and then move your cursor down to this little blue square in the lower right-hand corner, it makes a crosshair. And then if you double-click that, it should copy down.
Thank you.
It'll do that as long as the column next to it has entries in it. So now if we can do a very similar thing for the position, which is I go in that second box, I hit equals. So it's going to be the position that it was before, and then plus. Now remember, take the velocity from the previous row and multiply that by the change in time. So that's going to be A3 minus A2. All right, so in the first tenth of a second, using this approximation, it doesn't move at all because the initial velocity was 0, and it hasn't changed yet. And again, we can copy down and make the plot of position versus time and move it to its own sheet. So we can see that it has this parabolic trajectory, and we could see, well, okay, if 0 is the ground, then we'd have to really stop after like 5 seconds because that's where it appears to hit the ground. But the equations don't know anything about that, right? So it just goes there. Okay, so one nice thing that's about this setup is that you can now use this. Okay, so let's start, rather than starting at rest and just falling down, we can change the initial velocity. So let's make it, if we make it 10 meters per second, just change that, everything updates. And I can look at my velocity versus time graph, right? I can see that it starts at 10 and goes negative, goes towards 0, then eventually negative. And well, on this scale, 10's not that big, so maybe let's make it 100. See what that looks like. Yeah, so you can see that it goes up, and then after about 10 seconds, it reaches its maximum height and starts going back down. Right, so all this stuff that we knew from kinematics. So now we could do this using a computer programming language rather than Excel, but we'd be doing the same calculations. We'd be saying, hey, go back to that list. What was the acceleration a second before? Multiply it by the change in time. What was the velocity from the second before, or from the step before? Multiply that by the change in time, and use those to update what our velocity and our position values are. And so, as I said, it's nothing fancy. We can do it with good old or terrible old spreadsheets, whatever your feeling is. Some people love using spreadsheets, or you could do it using your favorite computer programming language. It's the same math. Okay, we'll come back to that in a minute with a more interesting problem that you probably haven't solved before. All right, so let's add a drag force to this, right? Because that's something that in an intro physics class, they always say, well, let's ignore air resistance, right? It's too hard. And why is it hard? Well, let's start with linear drag, which we talked about a little bit in class last week, I think it was. Right, so the force of, we call it linear drag because it depends on velocity to the first power. Right, so our total force now is going to be, we still have negative mg, right? We have the force of gravity, but then we also have this force that points opposite to the velocity. So that's why there's a minus sign. And then there's some constant b that that characterizes, the size and shape of the object. Right? It has units. Well, it has the units that it needs to make that be a force when you multiply it by velocity, which turns out to be kilograms per second, which is a weird sounding unit, but that's just what it is. And then if we calculate the acceleration, we just divide through by mass. And then we get that the acceleration is negative g. And now we're going to have also this negative b over m times velocity. Okay, so let's go back to our spreadsheet and see how we can incorporate this additional force to our spreadsheet. All right, so we're going to use b over m equals 0.3 because I tried that ahead of time and found that that was a good one to use. Okay, so the first thing that we need to do is clear this acceleration column. So you can either right click and hit clear column. Don't hit delete column because that'll just get rid of the whole column. So clear it, or you can just highlight it and hit the backspace or delete key on your computer. Okay, so replace the acceleration there. Okay, so the acceleration, well, in the first step, because remember the velocity always depends on what, oh, and let's also start with the velocity, go back and make our initial velocity 0 just to start. Okay, so the everything depends on the previous step. So we have to kind of do that first step is just going to be g, right? Because the acceleration is never 0. Now starting in the second line, we're going to have equals negative 9.8, so that's our g, and then minus, right? Because there was a minus in the equation, minus 0.3 times the velocity on the previous step. Okay, the initial velocity was 0, so that's still going to be negative 9.8. But now when we copy down, we can see everything fills in. So all we had to change was what the acceleration expression is. And then the velocity and position columns are going to fill in based off of that. So if we go to velocity versus time, we can see that it starts out negative and starts approaching some constant value, right, a terminal velocity. If we look at the position versus time, we can see it starts out kind of looking like a parabola, but eventually goes toward a constant slope, which is what would happen if you are moving at a constant velocity. Right, so it looks as we expect. Now it's interesting or worthwhile to plot acceleration versus time. Right, so we can see that the acceleration starts out, well, let me move it to its own sheet. The acceleration starts out at negative g, but then eventually tends towards 0, right? And that makes sense because terminal velocity is when the downward force of gravity gets balanced out by the upward force of the drag force, right? And so when the forces are balanced, the acceleration becomes 0. Try just playing around with different initial velocities. So try, putting in something that is so that it looks like the terminal velocity is something like negative 32 meters per second. So try putting in, like say a negative 50 and look at your charts or your graphs. Try putting in something positive, see what happens. So just kind of play around. All right, I put started with velocity of negative 50, so you're exceeding the terminal velocity. You need to give me access. If you go to the top right and say anyone with the link, or I can just request access. So yeah, so you start out exceeding terminal velocity, and then you approach it from the other side. Oops. Yeah, position versus time, it's almost linear right away. Acceleration versus time, first you're going to have a positive one because you're slowing down, and then it goes back towards 0. Okay, so I mean, now you have what amounts to a solver for linear drag, right? Based on, and now it's not perfect. It's going to make some error based on the fact that you're doing finite step size, but it's probably better than you could do, trying to calculate using calculus. You could make it better by replacing that time column. Rather than doing every 1/10 of a second, you could do every, 0.05 or every 0.01, and that would make it an even better approximation. And probably for an assignment at some later point, I'll have you play around with looking at, how that affects how accurate your approximation is. Okay, so now the last part of this, and I'm going back to slides here. So that was with, a particular starting velocity, a particular value of b over m. So, if the shape or, whatever the value for b is going to be different, or the mass is going to be different, you would have to redo your spreadsheet, right, for all of these different possible values. And that's annoying. So we would like to do something more general or universal, which we do by making our equations dimensionless, right? So this is, something that we talked about in terms of looking at scaling, but it's also really useful for doing computational work, because it allows you to say, well, rather than trying this for every combination of different constants, I can do it once, and then if I have a particular thing that I need to get real values about, then I can convert it. So our equation for the acceleration has units of meters per second squared. So if I divide through by g, as I've shown here, every term is dimensionless now, right? So acceleration divided by g, then I've got b times velocity over mg. You can check the units on that. Is going to be dimensionless, and then of course 1 is dimensionless. So this tells us, or this suggests, that b over mg, or I guess I should say mg over b, has units of velocity. And we could call that a characteristic velocity, but we can see by looking at the scaling argument that that's going to give you your terminal velocity, right? And so our scaling argument, right, when we have things that are subtracted, we can tell that when, just if you put in vt is equal to negative of that, then the acceleration will be 0, right? So if it gets a little bit bigger than that, then you're going to have a negative. If the velocity is a little bit bigger than that, you're going to have a positive acceleration. If the velocity gets a little bit smaller than that, it's going to be a negative acceleration, right? So that's our characteristic velocity. And we can find a characteristic length and time. So tau is a characteristic time, chi is a characteristic length, just based on saying, well, what constants do I have? I have b, I have m, and I have g. And how can I arrange them using dimensional analysis to give units of time and units of length, right? So I didn't show the work on that, but that's exactly how I did it, just like you did in the first homework assignment. And you can see that if you do chi over tau, that will give, that's going to give you, right? So it's a length over a time. That's going to give you the terminal velocity. Now I just realized I did a bad notation here. I'm gonna fix it. That's the nice thing about. Okay, so rather than, I'm gonna call this TC for characteristic time. And XC for characteristic length. And then I have dimensionless variables. Tau is time divided by the characteristic time. And chi is position divided by the characteristic position. Okay, that's valid now. So my dimensionless acceleration is the second derivative of chi with respect to tau, but it just gives me back the original, the first line there, really, except instead of writing b over mg, I've written v divided by vt. Right, so now I can just take this equation, right, and say my acceleration is, -1 instead of negative g minus this dimensionless velocity. And so now I have something that's more general. So it's going to tell you, rather than plotting velocity in meters per second, it's going to plot velocity in units of that characteristic velocity, and position in units of that characteristic length.
Your film is now ready to be shown.